Right. Now we are going to see what is LPP. In the previous class, we saw what is graphical solution. Now, graphical solution, the number of variables is restricted to two variables. Here, when the number of variables is more than two, how to go about it? So we use a method which is known as simplex method. That is the next simple, widely used methodology. So now, in order to do the simplex method, we need to know certain basic definitions and certain. Okay, so what are the forms that are required? Like you have something called as a canonical form, standard form, and then one main constraint is our variables should be greater than equal to 0. Suppose nothing is told about the variable, then how are we supposed to proceed with it? All these things we'll see. Okay, so on a linear programming problem, first thing what we are going to do is, this was told yesterday itself, we are just refreshing, right? So canonical standard forms of LPP. The canonical form, yes, I want everybody to mute yourself. In the canonical form, the problem is always a maximization problem. Okay, problem is always a maximization problem that has to be taken care of. Okay, so it always has to be a maximization problem. For example, see, if it's minimization, you have to convert actually. So it should be a maximization problem, and all your constraints, look at the constraint here, should be of the form less than equal to. The problem should be a maximization problem, and all the constraints should be less than or equal to. So we have maximize z is equal to c1x1 plus c2x2 plus etc. cn xn, subject to a11 x1 plus a12 x2 etc. a1n xn, which is less than equal to b1. So all the look at the second line, it is less than equal to b2. So we have up to m rows in our matrix. So we have m such equations, and this non-negativity constraint is a must. And non-negativity constraint, all your xi should be greater than or equal to 0. So if these conditions are satisfied, then this form of LPP is called a canonical form. So canonical form means problem should be a maximization problem. All your constraints should be less than equal to, plus all your xi's are greater than or equal to 0. Then suppose you want to write this in a matrix notation. So it could be very well represented as maximize z is equal to cx subject to ax less than or equal to b and x greater or equal to 0. So here your matrix is a11, a12, etc. a1n. There are m such rows ending in am1, am2, etc. amn. X is nothing but a column vector. How many columns are here? N columns. Correspondingly, you have x1, x2, etc. up to xn. What is b? B is the constant which is going to be present. See, look at this slide. B is b1, b2, etc. bm. This column vector. So b will be the column vector b1, b2, etc. bm. Keeping this in mind, the problem is reduced to or represented as maximize z equal to cx subject to ax less than equal to b and x is greater than or equal to 0. We have in our objective function, look at this, c1 x1 c2 x2 etc. cn xn. All these ci's are the costs that are being attached to each of these variables xi. So these also should not be negative. Generally not negative. In certain cases, yes, it may be negative. So C is also represented as C1, C2, Cn as an n tuple. Okay. Next. Characteristics of the canonical form. So what are the main characteristics of this form? The objective function is of maximization type. All the constraints are less than equal to, and all the variables xi are non-negative. Then what we saw before was canonical form. What you are seeing now is the standard form. So in standard form, what is the difference? The problem is maximization only, same as before. Please look at this inequality. There the inequality was less than equal to. Here there is no inequality. Everything is equality. You have a11 x1, a12 x2 plus a1n xn equal to b1. Similarly, a m1 x1 plus a m2 x2 plus a mn xn equal to bm. And what is the non-negativity constraint? All your xi's are greater than equal to 0. So this is the main difference between your canonical form and the standard form. What we can ask? We can give you, if the constraints are having only equal to constraint and the problem is a maximization problem, then the representation is number 1 normal form, number 2 canonical form, number 3 standard form, number 4 matrix form, something. So you have to tick standard form, probable MCQs. Okay, and the non-negativity constraints x1, x2, xi are greater than equal to 0. So this is known as standard form. Next, what is the characteristic of the standard form? The objective function is maximization. All the constraints are expressed as equation. This is very important. Okay, I have written R twice, only one is taken. All constraints are expressed as equation. Then all the xi's are non-negative, and this is also important. Right hand side of each constraint is non-negative. That means, what is the right hand side? All your PI's. All your PI's are non-negative. That is the meaning. Okay. Next. Now, what all we have to keep in mind before converting a given problem into a canonical form or a standard form? The first thing what we have to remember is, suppose you are given minimization. I am going to talk about the amount that I have to spend to run an industry. So I have to only minimize the amount. There is no point in saying that I have to maximize. So how will I convert it into maximization? So we can use the first point. The minimization of a function f of x is equivalent to the maximization of the negative expression of the function. Look at this, minimum f of x equal to minus max minus f of x. So if z is equal to f of x, if I take z equal to f of x, then I will have minimum z is minus max minus z. So I can make use of this, convert the given minimization problem into a maximization problem. Then, what is the second point? An inequality in one direction can be converted into inequality in the opposite direction by multiplying both sides by minus 1. This all of you know. If I have an equation ax1 plus bx2 greater than or equal to c, if I multiply this equation by minus 1, I will get minus ax1 minus bx2 less than equal to minus c. I just multiplied right side and left side by minus 1, so I am getting this. Okay. Next, an equality constraint can be expressed as two inequalities. That means if you have equal to, what does it mean? It will also fall under greater than equal to category. It will also fall under less than equal to category. Then I definitely say it has to be equal to only. Isn't it? How you will think about this? Now you remember we did graphical method. We had, let us say, x1 axis. We had, let us say, x2 axis. Suppose I want to draw the line x1 equal to x2. Obviously, x1 equal to x2 is the straight line which I have drawn, which is inclined at 45 degrees to both the x1 axis and x2 axis. Now, how I can represent this? My x1 is greater than or equal to x2. If x1 is always more than my x2, where will that x1 lie? x1 is more than x2 means it will be this particular portion. Suppose I am going to use x1 less than or equal to x2. I have x1 less than or equal to x2. Always x1 is less, x2 is more means it should go in this portion plus this line. Plus it will also take the point on this line because it is less than equal to. So what is common to both this and this? It is only this particular straight line. That means it is nothing but the equal to notation. So if you want to change this equality to inequality very easily, you can rewrite it as using both greater than or equal to and the less less than or equal to inequality, then you will get equal to. Next, an inequality with its left hand side in the absolute form can be represented as two inequalities. What you will do, you will just make use of, once again, mod format. Mod means absolute value. If suppose x is positive, see, I will have mod x is greater than 5. Suppose I tell x is positive. Suppose let us keep x as positive. Then what can I say? Immediately I claim x is greater than 5. Suppose I say x is negative. Then what I will tell? I have minus x, but I know definitely minus x is strictly less than 5. It's a negative quantity. So the same concept you can apply over here, because minus x less than 5, then x is greater than minus 5. So what happens? I have x is greater than 5 and x is greater than minus 5. Same way, x is nothing but ax1 plus bx2. So ax1 plus bx2 is less than equal to c. Similarly, ax1 plus bx2 is greater than or equal to minus c. Any problem? You are able to get this? If you are not able to get this, please tell me. Yes, the last property, if you are able to follow, yes. If you are not able to follow, please tell me. Hmm. You don't have to take down these things. These things are recorded and the word format of this is there in your GCR. I have posted today somewhere around 11:30. Okay. See, reasoning is like this. I have mod x is less than equal to 5. Let me say capital X. Mod, or let me even take it with more symbolic relevance. Mod x less than equal to c. So if x is greater than 0, this implies my x is less than equal to c. Suppose my x is strictly less than 0, this implies minus x. What will happen if x is less than c? Definitely minus x is also less than equal to c. Now let me take my x is equal to ax1 plus bx2. So this implies my ax1 plus my bx2 value is less than equal to c, and I also need to use the same notation which is over here. When I multiply both sides by minus 1, this implies my x is greater than or equal to minus c, or I have ax1 plus my bx2 is greater than or equal to. Now it is clear? This is how I got that property. Next, number 5. If a variable is unconstrained or unrestricted means we don't know whether it is going to be positive or negative. Okay, so it can always be expressed as a difference of two non-negative variables. So I can do my x2 equal to x2 prime minus x2 double prime. So what happens? Suppose x2 prime is bigger than x2 double prime, x2 is positive. Suppose x2 prime is smaller than x2 double prime, x2 is negative. Accordingly, we can fit the values. Then, what happens in the final case? All my x's are greater than equal to 0. So, I can revert back to the canonical form or the standard form as I need it. Next, whenever the slack or surplus variables are introduced in the constraints, they should also appear in the objective function with 0 coefficient. So, how do we go about this? Do you remember what is slack and surplus variable? Suppose we are having ax1 plus bx2 is greater than or equal to c1. Let me say and then I have a1 x1 b1 x1 greater than or equal to c1. Let me say a2 x1 b2 x2 is less than or equal to c2. Now what I want to do, initially in any problem I want to convert inequality to equality. In this case it is greater, so I should subtract. So let us call this equation 1, let us call this the equation 2. So in equation 1, what I should do, I have greater than equal to, subtract S2 to make it an equality. To make it an equality. Okay. So what I am using here, this only counts. Subtract S2. So S2 is called surplus variable. So S2 is called the surplus variable. This is what we saw yesterday. So now what will happen? I will have AX1 plus BX2 minus this S2. I will minus approximately so that this becomes equal to C1. Therefore, this is called surplus variable. Similarly, we come for A2x1. Let us take A2x1 plus I have B2x2. I'm having less than or equal to C2. I have to add something. So let me say add S1 to make it an equality. Okay, so when I add this S1, what happens? Here I will have A2x1 plus I will have B2x2 plus I will have S1 equal to C2. So what is this? S1 is called your slack variable. So this is called your slack variable. Any problem? Everybody remembers now what is slack variable and what is surplus variable? If it's less than equal to, you add something, that is slack. If it's greater than equal to, you subtract something, that is your surplus variable. Okay, next. Now we are moving into the simplex method. So before going into the simplex method, if you want, you can give an intro. Otherwise, before going into the simplex method, we should know what is a basic solution, what is basic feasible solution, and so on. So why we need this simplex method? Actually, what happens is this is an iterative method. So when you write a program and you put it in a for loop, it keeps executing again and again, and this method, this algorithm will try to move from one vertex of the feasible region to another vertex. Because it's a convex region, it will move from one vertex to another, leading you to the optimal solution. So this is very useful with respect to programming. Okay, so under that, what is a basic solution? Given a system of m linear equations with n variables, the solution obtained by setting n minus m variables to 0 and solving for remaining variables is called a basic solution. The m variables are called basic variables and they form the basic solution. The n minus m variables which are put to 0 are called the non-basic variables. So we should know what is basic and what is non-basic. Okay, next. A basic solution is said to be non-degenerate solution if none of the basic variables is 0. Then a basic solution is said to be a degenerate basic solution if one or more of the basic variables is 0. We'll do a problem now and illustrate this. A feasible solution which is also basic is called a basic feasible solution. Okay, so now we'll take a problem and we'll try to solve the problem and get the Basic solution, basic feasible, check whether it is feasible, basic feasible, degenerate, all that we'll check. First, we'll try to write the given problem in a standard form or canonical form. Sitting on. Express the following LPP. This you have to write. Express the following LPP. Express the following LPP in the canonical form. Express the following LPP in the canonical form. So how we are going to express? Take down maximize z equal to, I have 2x1 plus 3x2 plus x3, 2x1 plus 3x2 plus x3 subject to 4x1 minus 3x2 plus x3 less than or equal to 6, x1 plus 5x2, x1 plus 5x2 minus 7x3 greater than or equal to minus 4 and x1 comma x3 greater than or equal to 0. So now what happens? Nothing is told about x2. So x2 is unrestricted. So x2 is an unrestricted variable. So this is what is given to you and I want you to write it in the canonical form. So how do we write this in the canonical form? The first thing what we have to do is we need maximization function. So first step is clear. Given problem itself is a maximization problem. Then what has to happen? All your inequality should be less than equal to. So multiply the second inequality by minus 1. Then x2 is unrestricted. So write it as a difference of x2 prime and x2 double prime. Okay. So we will take the solution in a new sheet. So solution x2 is unrestricted. x2 is unrestricted. So I should write my x2 as x2 prime minus x2 double prime. This is the first step. Also change all inequalities. Also change all inequalities as how to change less than equal to. So now how we are going to do this? Our function is maximize z is equal to, so I have maximize z equal to, I think 2x1 plus 3, x2 should now become x2 prime minus x2 double prime plus I have an x3 plus x3. Then what I have? I have my constraints subject to, what is the first constraint we are having? 4x1 minus 3 into x2 prime minus x2 double prime plus x3 is less than equal to 6. Now come for the second equation here. What happens? It is of the form greater than equal to. So multiply, you write in your notebook, multiply the second constraint by minus 1. Okay, so we multiply the second constraint by minus 1. So when I multiply this by minus 1, I have minus x1 minus 5 times x2, but x2 has to be replaced by x2 prime minus x2 double prime. So minus x1 minus 5x2 plus 7x3 plus 7x3 is less than or equal to minus of minus 4 is plus 4. So now what are the constraints I have? x1, I have x2 prime, I have x2 double prime, comma, x3 are all greater than or equal to 0. Since this is true, this is our required canonical. People are able to follow? Okay. Once I finish, you tell me, then we can move to one problem in standard form and then we'll do sums for basic solution. Can anybody represent this in the matrix form for me? Can anybody represent this in the matrix form for me? Yes. You should tell me what is my A. First thing what you have to do is you have to tell me what is my A. Then you have to tell me what is my X. Then you have to tell me what else you need to tell me. You should tell A, you should tell X, you should tell me my B, and then finally you should tell me my C. Yes. Who will tell me what is A? What is the dimension of A? 3 You should take only constraint. So what is the dimension? 2 rows. How many variables are there? 2 into 3. No, we have changed to x2 prime, x2 double prime. No, so 2 into 4. 2 into 4. So what will be the value? My first row will now become, I will have 4 for x1, then coefficient of x2 prime minus 3, x2 double prime, value is 3, then I have x2, value is 1. Then what is the second row? Minus 1, then I have minus 5, then I have 5, then what else I have here? 7 plus 7. Now I have to write my vector x. What is my vector x now? x1. I have x2 prime. Then I have x2 double prime. Then I am having x3. Now what is my b? My b is only 6 and 4. My b is only 6 and 4. Now what is my c? C is the cost function. So 2, 3, minus 3, 1. So it is 2, 3, minus 3, 1. This is my C. I am reading everything from this slide. What you have over here for the inequality, that coefficients
The second row is supposed to be minus 1 the matrix.
in the matrix. So second row, here it is 1 only, no? So what did I put? I put 1 only. Correct only, no? Just check, I can view the matrix now. 4, minus 3, 3, 1. x3 is only there now. Minus x3 is not there. So it's correct. Okay. So this represents the matrix form. So what is the matrix form? With this details, my matrix notation will be, what is our matrix notation? Maximize. Ah, that, that
Second
second
row,
row.
second row, first row.
It is minus 1, minus 5. Oh, I put 1. yes, it is minus. I have multiplied the inequality by minus 1. No, thank you. Right. Maximize z equal to cx subject to what is our constraint? Ax is less than equal to b, where all our xi, comma, our xi dash, comma, our xi double dash are all greater than. So this is no required matrix representation. Any problem? People are able to follow? Okay. Can we go to next sum? Or should I wait? Hmm. Okay. Shall we proceed? Yes. Now, express the following LPP in the standard form. Express the following LPP in the standard form. Take down. Maximize z is equal to, no, we'll go for minimization. Minimize z equal to, we did one maximization, no. So minimize z is equal to 5x1 plus 7x2, 5x1 plus 7x2, subject to x1 plus x2, subject to x1 plus x2 is less than equal to 8, 3x1 plus 4x2, 3x1 plus 4x2 is greater than or equal to 3, 6x1 plus 7x2, 6x1 plus 7x2 is greater than or equal to 5, x1, x2 greater than equal to 0, x1, comma x2 is greater than or equal to 0. So in this solution, what we are going to do is, first we need standard form. Since we need standard form, so in standard form, what can I say? In standard form, change inequality, change inequality to equality, change inequality to equality by adding slack and surplus variable, by adding slack and surplus variable, by adding slack and surplus variable. Okay. So what we are going to add? Well, then what more we have to do in this question? This question is a maximization. Also change, what should I change? Minimization problem into maximization problem. Also change, what to do? Change the minimization problem into a maximization problem. Into a maximization problem. So how we are going to change this minimization problem into a maximization problem? So we have minimum z is 5x1 plus 7x2. of z star would be equal to minus, what will I have here? Minimum of minus z is minus max of minus z. So what should I have here? I will have in the subjective function minus 5x1 minus 7x2. Okay. Then what I need, I have to find constraints. So in the constraints, I will have subject to come to the first constraint, it is less than equal to. So I will have x1 plus x2. I will add s1 equal to 8. Come to the second constraint, it is greater than equal to. So 3x1 plus 4x2 minus s2 equal to value is 3. Then come to the third constraint, 6x1 plus 7x2 plus 7x2 minus s3. What is this value equal to? 5. Now when I do this, for all this s1, s2, s3, I should add in the function, objective function, with the cost 0. So here I will have plus 0 s1 plus 0 s2 plus I will have 0 s3. So now I am done with all this. I have all my xi greater than equal to 0. Then what more I have to mention? S1 is slack variable. S1 is a slack variable. Then S2 comma S3, S2 comma S3 are surplus variables. What you subtract is surplus. Are surplus variables. And this is the required standard form. So in the standard form, all your inequalities should be made as equalities. How you make it as equality? You add slack variable and surplus variable. Okay? Any problem? And one more thing, however you write Si, these numbers are also greater than equal to 0. So Si comma Xi greater than equal to 0. Okay? You are following? Audio, video, everything is clear?
Yes, ma'am.
One more last problem for today. Find. Can I move the slide? Find all the basic solutions to the following problem. Find all the basic solutions. Find all the basic solutions to the following problem. So now let us see how we are going to go about it. Take out maximize z is equal to, it has got three variables, x1 plus 3x2 plus we will have 3x3 subject to, look to the constraint. I'm having x1 plus 2x2, x1 plus 2x2 plus 3x3 plus 3x3 equal to 4. Then 2x1 plus you will have 3x2 plus 5x3, 3x2 plus 5x3 equal to 7. All xi are greater than equal to 0. All xi's are greater than equal to 0. Find Which of the basic solutions find which of the basic solutions are basic feasible, comma, non-degenerate basic feasible, comma, optimal basic feasible. Optimal basic feasible. Now what we have to do, how we have to do. I'll give you the solution procedure, you start solving. We have two equations. We will take this as equation number 1. We are going to take this as equation number 2. We are having xi greater than equal to 0. Right. So what we do is, we have two equations, 3 variables. What should I do here to solve? What should I do to solve? I want to solve these two linear equations. I have 3 variables, only 2 equations. What I should do? What should I do? You have n equations in m variables. Set n minus m variables to 0. So we have only 2 equations, 3 variables. So my n minus m will be 3 minus 2 equal to 1. So put any one variable 0. Put any one variable xi equal to 0. Now we have 3 cases. In the first case, what I will do? I will put x1 equal to 0. When I put x1 equal to 0, what am I getting here? 2x2 plus 3x3 is 4. So I have 2x2 plus 3x3 equal to 4. Then what happens to the next equation? 3x2 plus 5x3 equal to 7. Solve. Give me x2 value. Give me x3 value. Then come for case 2. I'm going to put x2 equal to 0. When I put x2 equal to 0, what will I have? x1 plus 3x3, x1 plus 3x3 equal to 4, and I will have 2x1 plus 5x3, 2x1 plus 5x3 equal to 7. Solve. Give me x1 value, x3 value. I know x2 is 0. Then come to case 3. What is case 3 for us? Case 3 is, I will put x3 equal to 0. So when I put x3 equal to 0, what will I have? 2x2 plus 3x3, 2x2 plus, I will have the first x1 term for me. 2x2 plus x1 equal to 4. 2x2 plus x1 equal to 4. And what is the second one? 2x1 plus 3x2. 2x1 plus 3x2 equal to 7. Now give me x1 value, x2 value. Here what will happen? 2x1 means 4x2. So 4x2 means 4x2 and 8. 4 means x2 is 1. If x2 is going to be 1, x1 is going to be 2. So 2 into 2 is 4 plus 3 is 7. So now look at this. I have x3 0, x1 2, x2 is 1. Here, what are my basic variables? Here the basic variables are the ones which I don't put 0. Here the basic variables are x1 equal to 2 and x2 equal to 1. They are not 0. Therefore, what is the solution? What is the solution here? You should only tell me. I put x3 is 0. I am having all other cases. So, what is the solution? The solution is, it is feasible. Is it non-degenerate solution? And it is also feasible and optimal. So, write down this solution, what can I say? This solution is basic, feasible and optimal solution. It is an optimal, basic, feasible, non-degenerate solution. What do you mean by non-degenerate? Basic solution is non-degenerate if none of the basic variables are 0. So x1 is not 0, x2 is not 0, therefore it is basic, feasible, non-degenerate solution. Basic, feasible, non-degenerate solution. Any problem? Only if you know your definitions, you can answer the questions. Now, we have to do the same thing for case 1 and 2. If you have 2x2 and 3x3, so I have to multiply the first equation by 3. I will have 6x2 plus 9x3 equal to 12. Then here I will have 6x2 plus I will have 10x3 equal to, what will I have? Yeah, multiplying by 2. 14 minus 1. Yeah, x2 is minus 1 and x3 is 2. So this is also non-degenerate basic feasible solution. So this is basic feasible solution and it is non-degenerate. Then come for the next one. I think x3 is 1, x1 is also 1 now. So this is also a basic feasible solution and it is also a non-degenerate solution. Is it correct? Yes or no? Correct? Now tell me, what is the optimal solution? What will be the optimal solution? In the first case, what is the value of z? Yeah? Z is minus 1 and 2. Minus 1 is minus 3 plus 3. Check. Minus 3 plus 3 gone case. Z is 0. In case 1, I get my z value to be 0. In case 2, I have 1 and 3. 1 plus 3 is 4. So I have z value to be 4. In case 3, what is z value? I have x1 is 2 and x2 is 1. So here I am having z is equal to 5. I am substituting in the main equation. Okay. Since z equal to 5, this is the optimal solution. This is the optimal solution. Why? Because we are doing maximization. Our max z equal to 5. Therefore, this is the optimal solution. Okay? Since maximum z equal to 5 and this maximum z equal to 5 occurs only for the third case, we are doing the maximization problem. Therefore, this is the optimal solution. Yes, I think I have to take attendance. Correct? That's what. That is number 1. Yes, ma'am.